So Roberta, I guess in 1 minute, we can start.
1 minute more. Okay, thank you.
Oh, good day, Roberta. Nice to see you.
Nice to see you. Just a minute. When it's time to start.
Roberta, can you hear me?
Yeah.
Okay, good to see you.
Nice to see you.
Good,
Unfortunately, I was on holiday. I just came back yesterday to the lab.
That's
So
good, good,
I've not
very good.
attended the entire conference, but I hope that I can have access to some of the recordings. Sorry.
Oh, good.
I guess we can start.
Okay, Dmitry, many thanks. So, good afternoon, everybody. Thank you for having conveyed back to the conference for this, say, very last session. Last but not least, it seems that we are going to have a very interesting session. And I do not want to steal any time to the first speaker, that is Alexander Schnegg from the Max Planck Institute in Mülheim. He's going to talk about, say, a high frequency EPR spectroscopy for the determination of very large zero field splitting in metal ions. Thank you, Alexander.
Thank you, Roberta, for your kind introduction. I also would like to thank the organizers of this conference, particularly Sergei and Matvey, for providing this really nice frame. And I also I'm very thankful that there was also a very appropriate frame to say goodbye to Konstantin Ivanov, who was, as you all know, one of the really important examples of the great magnetic resonance school in Novosibirsk, which fortunately continues, but even despite of the very unfortunate and much too early death of Konstantin. My talk today is entitled Breaking the Silence, Determination of Exchange in Zero Field Splittings. And the silence which I wanted to break with the methods which we developed during the last years are states with large spin couplings in different classes of transition metal ions. We are basically interested in a quite broad range of transition metal ion complexes. First, metalloproteins. Here depicted is the structure of myoglobin, where oxygen binding leads to change of the iron oxidation and spin state. The middle picture depicts a transition metal ion catalyst, the so-called Nuthera catalyst, which is a cobalt material, which is a self-healing oxygen evolution reaction catalyst. It's of course one of the most important research themes in transition metal ion research, to create earth-abundant catalysts to tackle pressing energy problems. And on the right-hand side is depicted an iron-6 complex, which is just an example for a molecular nanomagnets. And in all of these complexes and these classes of complexes, spin couplings provide very sensitive probes, both of the electronic structure as well of the atomic structure. And in addition, of course, spin coupling parameters also determine magnetic properties, which are determining the properties of molecular nanomagnets, but are also of great interest in proteins, where iron in particular serves as a prime contrast agent, for example, in functional magnetic resonance imaging to visualize brain function. And even in the case of catalysts, magnetic properties can be used to enhance and get additional insight into catalytic processes. Therefore, these are spin couplings in transition metal ions are highly desired pieces of information, which are determined or expressed and parameterized by a so-called spin Hamiltonian, which is shown here. This first term is the Zeeman interaction, describing this interaction of the spin with an external magnetic field. The zero field splitting, which is only present in systems with S larger 1/2, which expresses the interaction of electron spins on nuclei with more than one unpaired electron, spin-spin couplings, both dipolar or exchange interactions, and the hyperfine interactions of an electron spin with the nearby nuclei spins. And very important, all of these interactions contain a whole wealth of information, but they span a very large energy range, more than 10 orders of magnitude, where we find the hyperfine interactions and small dipolar couplings on the lower edge of this, what I would call an EPR method ruler, and the exchange interactions and zero field splittings on the high energy edge of the scale. And I don't want to go through all these acronyms and methods which have been developed to extract these properties. However, what I would like to mention already now is that there is no one single method which can determine all of these interactions, and therefore we have to properly choose our spectroscopic techniques. And today I will focus on the high energy edge, where high frequency and high field EPR methods are most useful for the detection of high spin states. I would like to recall where these actually already a bit outdated term of EPR silence in paramagnetic substances came from. Here depicted is again the Hamiltonian of the zero field splitting tensor, which can be rewritten in a form that it contains only two scalar components, the axial and the rhombic part of the zero field splitting. And there's an important difference between integer and half integer systems, which are classified as non-Kramers and Kramers systems. In non-Kramers systems, zero field splitting, if it is rhombic, can completely lift the degeneracy of the spin states, whereas Kramers systems remain degenerate even in the presence of rhombic zero field splittings. And this fact makes them detectable even at frequencies which are lower than the energy splitting of the zero field splitting, because this is the most important point, that this axial zero field splitting leads to a separation of the spin states, which can be larger than the microwave quanta applied in a conventional EPR spectrometer. This is shown here for the case of a simple iron porphyrin, where zero field splitting is typically in the range of several reciprocal centimeters, which corresponds to several hundreds or 100 gigahertz. And depending on the orientation, which is depicted here as blue and red bars, we find different field dependencies of the energy levels with increasing external magnetic field. And here the famous iron 3 S equals 5/2 EPR spectrum is shown, which shows typically, if in the absence of rhombicity, it shows a resonance at a G equals 6 value and a G equals 2 value. And from this serves as a fingerprint for these states. However, typically it's impossible to determine the zero field splitting parameter exactly from such spectroscopies. One then has to resort to other methods, like in the previous talk described squid magnetometry, for example, or neutron scattering. However, a precise determination of the zero field splitting parameters is still not simple, and Roberta is probably one of the person who mainly pioneered this field in studies already some years ago, where she showed that high frequency, high field EPR can be employed to determine large zero field splittings. What in principle, EPR experiments covering a broad transition energy and field range can be conducted at high magnetic fields. Sweeping the external magnetic field, similar to what is done in conventional EPR. However, our choice was to instead of sweeping the external magnetic field, we are sweeping the energy, and we are doing this because we don't know how large these transitions are, and therefore we keep the external magnetic field fixed and sweep the excitation frequency. And this then leads to spectra like this, which are again spectra from an iron 3 S equals 5½ macrocycle recorded with our frequency domain terahertz EPR spectrometer in Berlin. And these transitions contain now not only the G equals 6 line here at the low energy edge, you see a 263 gigahertz spectrum, which is really the lowest frequency which we employed here. But you can also excite directly the transitions from the MS minus plus minus 1/2 to 3/2 and 5/2 transitions. And from this, by simulating such a 2D plot, where here the energy is now swept versus the external magnetic field, very precise determination of the whole zero field splitting tensor can be obtained. And this is the scheme we are using, either the internal source of far infrared spectrometer or synchrotron source, which is necessary because we would like to access very low frequencies, which are difficult to generate with globar or sources or lamps. And then we use as a monochromator an FTIR spectrometer, from where we extract the radiation, feed it through the either perpendicular in Voigt or in Faraday or Voigt geometry through a superconducting magnet, which can be swept to 10 Tesla, and then detection happens via very sensitive bolometers. And we are now extending this system also to a field domain spectrometer, but I will not go too much in detail here in order to save time. Instead, I would like to show you a few examples of experiments which we did during the last time. Depicted here are the frequency domain spectra of a corol, which is also an iron macrocycle. Here, an iron is bound by 4 nitrogens, and in addition, different and this complex is differed in their 5th ligand. And these corols are very important examples for CO2 activation processes, and therefore the electronic structure is of great importance. And the important point in the states beyond iron 2 is the oxidizing equivalent sitting on the iron, or is it distributed over the macrocycle? And it turned out that this is something which can be very well studied with EPR by determining the zero field splitting. Depicted here are zero field EPR spectra. These are detected completely in absence of an external magnetic field, and already from this zero field splitting, one can see a split resonance, which is centered around D, and its splitting is 2E. This can be then done at higher magnetic fields to also obtain information on the G values, and to extract information on the and to assign the field dependence of these peaks. However, in principle, already the zero field spectrum is enough, and we found two values which were very different for corols containing phenyl as 5th ligand, as compared to systems containing chlorine as 5th ligand. Here, the axial zero field splitting is around 20, and here it is around 15 reciprocal centimeters. And by combining this with quantum chemical calculations, we could assign 2 different scenarios, whereas in the case of a chlorine ligand with relatively small zero field splitting, we find an iron 2,3 state coupled to a chiral radical, giving rise to S equals 1. In the other case of a phenyl ligand also leads to an S equals 1 state, but this now originates from an iron 4 state, which is where the electron is localized on the iron. And this shows how quantum chemical calculations and spectroscopy can very well be employed to first to benchmark each other and to extract these important pieces of information from high-spin transition metal ions and their complexes. The second example is a study which we did together with Schnegg, which was a single molecule magnet, now a cobalt-2 ion, which was bound in this complex here. The samples were synthesized in the lab of in the Kishkin lab in Moscow, and from these complexes we obtained quite normal, I would say, CW EPR spectra, which show this typical resonance of T equals 4, and we could obtain also a very nice terahertz EPR resonance around 75 reciprocal centimeters, and from this we could calculate, from simulation of these data sets, we could obtain the rhombicity of the zero field splitting tensor and also its G values. And then we actually, this was Sergei's idea, to dilute the system and to check whether we can reduce the line widths and the interaction between the cobalt ions, and therefore the zinc was replaced by cobalt was replaced by zinc, and then we thought, yeah, the lines would just narrow. However, upon dilution of the system, we saw a complete switch of the zero field splitting and also a switch of the EPR spectrum. And after some thinking and additional crystallography and quantum chemical calculations, we could assign this to a switch of the zero field splitting tensor, which was induced by changes in the structural environment of this complex. And this was something which we were quite busy for some time, but fascinated us. And I'm showing this this example because it also shows that zero field splitting is very sensitive on the environment, but the good thing is nowadays that its sensitivity can be used here again to benchmark quantum chemical calculations. What is shown here is the zero field splitting delta. This is the MS 1/2, 3/2 distance, both experimentally obtained and calculated. And in addition, the distance between this oxygen here and the cobalt. And one can very nicely see that both theory and experiment match very well, and they indeed both clearly reveal this structural change in the zero field splitting parameter and help to assign this to a defined structural change. And this is something which I think will be more important also in the future when such systems, when these capabilities can be employed to fine-tune and predict also the magnetic properties of such complexes. My last example is now a coupled spin center, which is a copper-copper dimer shown here. This is a model for dioxygen activation in copper metalloproteins. It's mainly, it comprises 2 copper ions in two S equals 1/2 states. And I'm emphasizing this because despite of the S equals 1/2 of these 2 copper ions, it has a zero field splitting of several reciprocal centimeters, which is somehow surprising because copper as S=1 system has no single ion zero field splitting. And this is something which was already determined earlier, but not really understood. And therefore, this whole study was conducted together with Jerome Spira from the Maya group in Göttingen, who also synthesized the whole family of these complexes. And what we wanted to do is to get more detailed insight into these complexes and their magnetic structure. This is, since it is S=1/2, the spin Hamiltonian has no zero field splitting. And in order to create a zero field splitting, exchange couplings are, of course, the first choice. And here the extended exchange Hamiltonian of such a system is shown, which contains the Heisenberg-van Vleck Hamiltonian, which is isotropic, the anisotropic exchange interaction, and the Dzieloczynski-Muria interaction. And of course, if you apply an external magnetic field, also the Zeeman interaction. Here again plotted are the energy levels of these systems versus the external magnetic field. As in the case here we have an isolated triplet as ground state, and the S=0 state as excited state. And how can we now probe and prove such a scheme and the differences in the energy levels? Well, we did simulations of these Hamiltonian and found that for certain interaction scenarios, these states start to mix. And usually one would assume that only transitions between these states, the delta MS transitions, are allowed, whereas the transitions to the excited states, the delta S transition would be forbidden. This is what we all learn in our textbooks, if we at least read only the first pages, but this is something which one would assume per se. However, with in particular, Dzieloczynski-Muria interaction is here very important. The states can be mixed in a way that these transitions can be visible, but it's difficult to measure this because the energy ranges of these transitions span a very wide range. However, we were successful with our terahertz EPR method. Here again are plotted terahertz EPR spectrum plotted versus the excitation energy ranging here from 0 to 18 centimeters, and also at very high frequencies, here ranging from 110 to 180 reciprocal centimeters. And one should note here that this is approximately 10 reciprocal centimeters wide, which is something like 300 gigahertz or something like 10 Tesla. So these are really broad lines in EPR. However, shown here are simulations with the spin Hamiltonian shown on the previous slide, and we can clearly assign these transitions to the delta MS transitions, which are just the triplet transitions, whereas these transitions correspond to transitions from the S1 to the delta S state. And this is something which is, I'm not sure if this has ever been shown before, that both the delta MS transition and the delta S transitions can be observed in the same system. And this constricts the possibility for the spin Hamiltonian, despite being quite large, tremendously. And there are, we tried different scenarios, but we are now quite confident that we found a spin coupling scenario which can is valid for these systems. And this is, of course, something which is difficult to obtain from squid magnetometry, for example, this precision of different parameters. And I'm already up with my time. I actually wanted to announce that there is on this beamline in Berlin, which is a joint activity of the Helmholtz Center and the MPI-KEC in Mülheim, a postdoc position available. I will, after my talk, put this information into the chat. If you're interested, please don't hesitate to contact me. And of course, despite I'm already a bit late, I would like to thank all the people who have been contributing to these works, first by co-authors Carsten Holdak and Joscha and Thomas, who helped me to build up this instrument and work on it. I have a long-standing collaboration also with Sergei. I have only shown one example of this study on the cobalt complexes. Sergei's idea really stimulated a lot of improvement also on this instrument and many new experiments. Have been working with the people in Tallahassee and Josh Tulsa at the Roosevelt University, with whom we did the Corol work. And more recently, I started to collaborate with Frank Meyer in Göttingen, and Eckhard Bill is a colleague of mine at in Mülheim, who continues to also significantly contribute to these projects. And I'm thankful to funding from German Research Foundation, Minister of Education of Research of Germany, and Max Planck Society, and the Helmholtz Center for accommodating beam time, because this is important for this experiment. Thank you for your attention.
Thank you, Alexander, for this very nice talk. I have many questions, but I have to first to give the word to Kira. I see you have there.
Okay. Thank you for your presentation. I would like to know just about cobalt complexes with different linkage. Okay.
This one?
This one, yes. This is the same phase, only the structure transition. This is different phases.
This is the same complex.
Mm-hmm.
Throughout all experiments. It's always the same cobalt in the same binding environment. What changes is that the binding structure of zinc is slightly different for cobalt and zinc. And there's somehow a slaving mechanism that if it's approximately at 50%, but I think this is more or less random. If the structure is dominated by the zinc ligation structure, the zinc ligation structure is superimposed onto the cobalt. It becomes a cobalt in a zinc environment, let's say, and this switches the zero field splitting. It's switching, yeah, and this is shown here by the structure.
This is
the same atoms
zinc,
in this.
The compound 1,0. This is it. Mixture with zinc is a structural compound. Yes.
Exactly. This is the dilution ratio. This is
okay.
only cobalt,
okay.
and this is
okay.
only zinc, which somehow doesn't exist. Therefore, it's only close to.
Okay. Thank
dilution.
you for this precision.
I mean, it exists, but it's EPR silent. Therefore, there is no magnetic resonance studies on the one.
I know.
I don't see, but I have a comment and a question. Actually, it's really fantastic that you can achieve 15 terahertz, if I have well understood.
Mm-hmm.
This will be fantastic. I'm thinking about a nickel 2 species synthesized in Mark Murray in Glasgow lab, mm-hmm. Where we have been using torque magnetometers to determine the zero field splitting. Mm-hmm. Because of course it's silent and it is 500 wave numbers and a pure spin one spin Hamilton, very fantastic. But my question is, when you go to very high frequency, I suppose that you are also affected by absorption of the electric field of the radiation, because now in this range you have a lot of vibrational modes that can be excited. So the spectra that you are reporting have been a subtraction taken at different fields in order to get just the magnetic parts, or you are just able to selectively have the magnetically induced transition?
Roberta, you are completely right. I skipped this due the time, but these spectra are obtained by dividing. It's not a subtraction, it's a division due to the fluctuations in the background, a division of spectra taken at two different magnetic fields.
Okay. Awesome.
And we do this exactly due to the reason you mentioned, that in principle, you can also divide two or subtract two temperatures, because if you vary the spin population, you get also an EPR signal. But then you have all these vibrational modes in your spectrum. And what is really interesting with this field division is that you are not only very sensitive to pure EPR transitions, but you're also very sensitive to spin phonon coupling, because you throw out everything which is pure phonons, but you get a splitting or an anti-crossing in case of spin phonon couplings, because then you mix your states. And this is something which we had a publication recently with Josh Telzer and the people in Tallahassee, where we have shown this for also different cobalt complexes. I think Joris van Slaren has also published this some time ago, but this is something which is, yeah, I think very powerful also for spin phonon couplings due to this fact.
Thank you very much. I cannot see any other raised hands. So I think we have to move forward. I thank you again. And well, let's hope that we can interact soon. And now I would like to introduce Dmitry Yakhvarov. He's going to talk about in situ EPR spectroelectrochemistry, so EPR combined with electrochemistry. The contribution is from the Arbuzov Institute of Organic and Physical Chemistry. So please.
Thank you very much, Roberta, for your very kind introduction. And before my presentation, I would like kindly to thank the organizing committee of this conference for invitation of me and to present for you this talk regarding our recent results in application of in situ EPR spectroelectrochemistry for chemical reactions. Here on this first slide, you can see the possible application of the electrochemical technique, which operates under electrocatalytic conditions. Here we use usually some metal complexes like the nickel and cobalt complexes, which can be electrochemically reduced to formation of high reactive metal zero species, which can react with different types of organic halides, white phosphorus, PCl derivatives, to give some target derivatives like the products of the cross and homo coupling and various phosphorus compounds. In order to save the time, I would like to refer you to our recent reviews, which are mentioned on the back of this slide, which has been published this year, and you can find easy all information about the elaborated electrochemical methods. Just to summarize and to give you some short introduction to my presentation, I would like to speak about the application of in situ EPR study for activation of some type of organonickel sigma complexes and investigation of the formation of the mechanism of formation of catalytically active forms on example of some pincer type complexes. Also, I would like to show you some results which were obtained by us in recent years concerning the application of electrochemical study for generation of various types of binuclear complexes, where we can change the spin-spin interaction and we can change the spin state of the metal complexes using the electrochemical techniques. And the third part and last part of my presentation will include some application of in situ EPR spectroelectrochemistry for observation of some superparamagnetic cobalt nanoparticles, which also can be generated in electrochemical way. Here I would like just to show you that the electrochemistry is a very powerful tool for preparation of various types of organometallic complexes. Here, for example, you can see the different types of organonickel sigma complexes containing nickel carbon sigma bond, which can be synthesized very easily using this electrochemical technique, with application of the electrochemical cell without separation of anodic and cathodic compartments, where the nickel metal anode reacts like a source of the nickel ions to the system. All these sigma complexes have been synthesized by us and isolated in pure state, and all of them were characterized by various methods, including X-ray crystal structure analysis. What is the problem for the chemistry of these complexes? Of course, these complexes are very stable on air and in water, and of course cannot be used like active form of the catalyst for other cross or homo coupling processes. For this reason, we found the way that, for example, the bromo anion, which is coupled to the nickel center, must be removed in order to generate the coordinately unsaturated nickel complexes, which can be easy coordinate the molecule of the substrate and then make the reaction of the reductive elimination with formation of new carbon-carbon or phosphorus-carbon or nitrogen-carbon bond. For this reason, we decided to apply the electrochemical technique for investigation of possible activation of these organonickel sigma complexes. Here you can see the cyclic voltammogram of organonickel sigma complex containing the mesethyl group at the nickel atom. Here you can see that if we scan the rate of the potential rate to the cathodic path, we see the peak C1 and C2. Peak C3 is absent in this case. We have found that when we reduce the complex with the transfer of one electron to the nickel center, we observe the elimination of bromo-anion with formation of coordinately unsaturated radical complex. Later, I will tell you how we can apply the in situ EPR spectroelectrochemistry in order to determine the position of this unpaired electron. Because here we have two possibilities. If this electron occupies the nickel orbitals with formation of D9 configuration, this is much more difficult for coordination of the substrate and to use this compound in catalytical cycle. In case of this ligand of this radical is located on the diamine ligand like bipyridine or phenanthroline or some other ligands which we applied, then in this case we can generate active catalyst for synthetic chemistry. Here, I would like now to move to the anodic process. In case we start the scan of the potential of the working electrode first to the anodic part, and then we are going back to the cathodic position, then we observe the appearance of new peak C3. This peak C3 corresponds to the reduction of the electrochemically generated by oxidation unsaturated cationic nickel mesethyl bipyridine complex, which is active species for the process of gamma cross coupling and also oligomerization postulated by Bruchert. Now I would like to move to the next slide, where I would like to show you how we can distinguish the position of this unpaired electron. We use it the organonickel sigma complex with phenanthroline as the diamine ligands as the model compounds for this study. Here you can see that after transfer of one electron, we observe the signal with G factor 2000. It means that after transfer of one electron, we have the elimination of bromo-anion with formation of radical complex. It was very difficult to understand what is the position of this unpaired electron, because the G factor is very close to organic radical bonded to the nickel and to the nickel D9 configuration. For this reason, we decided to generate the free phenanthroline anion radical in electrochemical EPR cell, and we determined the parameters of the free phenanthroline anion radical species. And from this study, we can conclude that this electron is located on the phenanthroline ligands in organonickel sigma complex, sigma complex. And moreover, we found that phenanthroline is still bound to the nickel center, which can allow the stabilization of this higher reactive active form of the catalyst for the following chemical process. Then just a short overview of application of some in situ EPR spectroelectrochemistry in order to understand what happens in case of organonickel sigma complexes containing the pincer type ligands when we activate this by the activated reagent. For this reason, we synthesized the different complexes containing different halides at the nickel center. And we decided to investigate the electrochemical properties of these ligands. What happens when we transfer one electron to the nickel centers? It was very interesting for us. All the details of this study you can find in publication which has had published a couple of years ago. Here you can see the combination of the cyclic voltammetry and the electrochemistry with the EPR study. For example, here for compounds of 2 and 3 containing the chlorine and the bromine, we observed the EPR spectra which correspond to the formation of some complexes containing the bromo and chlorides. On the next slide, I will show you the structure, because this is also, it was only observed the molecular rearrangement of these complexes. And moreover, here you can prove the presence of the halogen ligand, for example, here as exemplified by the structure of the spectra. You can see here the signals which correspond to the coordinated bromo anion with the spin 3 of half. Very interesting results were observed in case of complex 1 and complex 4. For these complexes, we observe the same product when we transfer one electron to, when we oxidize the species by the anodic oxidation. We were very surprised to find why so strongly bonded different ligands like fluorine and iodine can give the same compound in anodic electrochemical process. Then we decided to investigate in this study in more details. Here you can see that after the transfer of, after the removing of one electron in the case of complexes containing the chlorine and bromine, we get the oxidative form of the complex, which is transformed to the one form, what was with G factor 2.240, which was mentioned on the previous slide. In case of complexes 1 and 4 containing fluorine and iodine ligands, from the EPR in situ EPR study, we have concluded and we determined the mechanism of the oxidation of these species. For example, in case of complex 4 containing iodine, after the oxidation, this is normal reaction when the iodine is very easily eliminated from the complex. The formation of such unsaturated complex takes place, which can be oxidized, oxidized with formation of this compound of nickel 3+. In case of fluorine, when we remove one electron from the complex, this complex undergoes to the formation of such binuclear complex containing the fluoride Bridget bond. And after decomposition of this complex with formation of difluorine derivatives, we have the same compound like in case of iodine ligand. In this case, we can prove that the fluorine and iodine have the same behavior and have the same product, but different mechanism of formation of such intermediate. Coming to the second part of my presentation, I would like to show you some results obtained with the synthesized binuclear nickel complexes. Why we use the binuclear metal complexes for our study? Because these species can be considered like a secondary building unit for formation of coordination polymers. And the study of these species much more easy because these complexes contains only two metals bonded by the, in our case, the OPO organic ligands. Here you can see that, in case we have the two nickel centers bonded by the OPO organic ligands, the some interaction between the two centers must be observed. And we measured the magnetic susceptibility of the complexes, and we found that we have some very weak antiferromagnetic interaction between the two nickel centers at low temperature. Then, in order to determine the spin state of the nickel centers in the molecules, we also performed the field dependence magnetizations. As you can see here, it is saturated about 4.4 Bohr magneton in the magnetic fields, about 7 Tesla, which correspond to the spin 2 for wool molecule. It was interesting to investigate the electrochemical properties of these complexes, and we recorded the cyclic voltammogram of these species, and we found that on the CV curve of these binuclear complexes also were observed the peaks which correspond to the reduction of nickel 2. This is just shown as the model compound nickel 2 to nickel 0, and the second peak correspond to the formation of bipyridyl anion radical species by the transfer of the additional electron to the electrochemically generated nickel 0 complexes. It was interesting to perform the EPR, in situ EPR spectroelectrochemical monitoring of these compounds. Here you can see the very broad line which correspond to the nickel 2 plus centers and in the molecule. And when we apply the electric current towards these to the solution containing the nickel 2 complexes, we can very easily electrochemically generate nickel +1 D9 configuration species. Then next application of the electric current allow us to generate the compound containing the nickel 0. Then follow a reduction of this species leads to decomposition of the complex with formation of nickel 0 bipyridine anion radical complex. Then from this study, we can conclude that the application of the electrochemically can very easily be applied for generation of binuclear nickel complexes in different spin states and can be considered as the good way for the generation and elaboration of new methods for preparation of the electrochemically of the some magnetic molecules with electrochemically changing spin state. In the last part of my presentation, I would like to show you our very recent results, which allow us to apply the in situ EPR spectroelectrochemistry for observation of the cobalt nanoparticles, which can be generated in electrochemical way. For example, here, I would like to show you the cyclic voltammogram of just a simple cobalt dibromine salt. Here you can see the reduction of this compound with formation of cobalt 0, which is adsorbed on the surface of the working electrode. This peak, this is the peak of oxidation of the adsorbed cobalt, metallic cobalt on the electrode surface. Why we use bipyridine? We use bipyridine because if we add, for example, one equivalent of bipyridine ligand, we can stabilize the cobalt 0, which is generated on this peak. And you can see on the cyclic voltammogram, peak A1 is completely disappeared. And also there's some change of the morphology of the peak C1 takes place. Increasing of the concentration of bipyridine allow us to record some classical cyclic voltammogram, which is used and very usual for the cobalt dibromide bipyridine complexes. What we decided to do? We decided to apply the cobalt dibromide with one bipyridine complex in order to try to generate the cobalt nanoparticles. For this reason, we performed the electrochemical reduction of cobalt dibromide in presence of one equivalent of bipyridine in situ EPR spectroelectrochemical cell. Here you can see the EPR spectra of the superparamagnetic resonance of cobalt particles, which were observed in the reaction mixture. Moreover, I would like to show you that this line is shifted to the smaller values of the magnetic field, and the broadness is strongly increased. It's strongly increased during the time of the electrolysis. And after performing of some time of electrolysis, which was calculated to the amount of the used cobalt dibromide and bipyridine complex, we observed the new line in which we can see all the types of the cobalt complexes which can be electrochemical generated in electrochemical cell. For example, here this line is correspond to the metallic cobalt, which is absorbed on the surface of the working electrode. This line corresponds to the cobalt nanoparticles, and this small line corresponds to the mononuclear cobalt 0 bipyridine complexes, which are generated in the electrochemical system. This just I would like to show you some very interesting experiments how we can generate the cobalt nanoparticles in macro scale way, based on the result obtained by in situ EPR spectroelectrochemistry. This is a normal laboratory made, handmade, we can say that the electrochemical cell with separation of cathodic and anodic compartments. Here you can see that after transfer of some amount of electricity, the cathodic part becomes darker, which contains some amount of the cobalt nanoparticles. And here, after the electrolysis, we can obtain very dark solution containing the cobalt nanoparticles. How to determine what type of the cobalt nanoparticles we obtained? We decided to apply the method of the small angle X-ray scattering analysis for determination of the size and the form of the cobalt nanoparticles. And based on the results, we have concluded that this electrochemical way allow us to generate the cylindrical cobalt nanoparticles with 9-10 nanometers in diameter and with the length 32 nanometers. All the details of these experiments you can also find in our publication, where all experimental results and the all observation of these electrochemical systems are discussed. And finally, I would like to thank that colleagues from different organizations of the world with whom we have nice collaboration, and especially the people who were involved in this study. And of course, I'm sincerely thankful to all of you for your kind attention. Thank you very much.
Okay, sorry, was muted. Thank you very much for this nice presentation. And we have two hands that are raised. Let's start from Kira again.
Okay, thank you for this interesting talk. Could you please to switch off the slide for where is the phenanthroline nickel complex?
Okay. This one?
I have a question. Why your theoretical spectrum generated from separate phenanthroline have more thin structure than those for complex?
Mm-hmm. Because it was very easy or difficult to obtain the pure spectrum, because in the system, the phenanthroline anion radical can react with the starting form of phenanthroline, and the electron is moved between the different molecules. And
okay.
also, yes.
Thank you.
Mm-hmm.
So we have another question from Michael Bubnov. Can you unmute yourself? Okay.
Yes, I have two questions. Dmitry, thank you.
Please a little louder.
Huh? Louder?
Louder,
Okay.
yeah.
Dmitry, thank you for your presentation. I would like to ask the slide number 9. Yes. Please comment where do you think the unpaired electron is localized in this system?
On the nickel center.
On the nickel center.
Yes, because this is the nickel 3+ for this compound.
Why,
or we can consider this one by.
But why you don't observe the splitting on phosphorus nuclei? It is too close to the paramagnetic center.
But unfortunately, we were not able to observe this splitting.
Nevertheless, you observe the iodine in the case 3. Am I right?
Iodine is eliminated on the first stage here,
okay.
when we transfer one electron for oxidation.
Okay, thank you. And the next question is to the slide number 14.
14.
Yes. The up spectrum, nickel 2+, do you think that it is the nickel high spin in the solution?
Yes, this is a nickel high spin. Because the broadness is very high. This is for nickel 2+ with spin 1.
Thank you.
If there are no more questions, I have a short question. When you form the nanoparticles, can you can you stabilize them by adding like a surfactant, or is just the BP that is acting as a, as a protecting
Yes,
layer?
yes. This is very good question. And the nanoparticles is stabilized by pyridine.
Okay.
Mhm.
Okay. So the measurement that they are stable then in air?
No, the measurement were performed in the sealed capillaries on the inert atmosphere.
Okay, so
Because
then the X-rays analysis have been done, everything I would say in situ. Okay.
no, this was after the generation of cobalt nanoparticles here, this under the nitrogen. This very carefully were moved to the capillaries, special borosilicate capillaries, and then the capillary was sealed. And then yes, and this capillary was used for the nanostar SAX experiment.
Okay, thank you very much.
Thank you.
There are no other questions. I think that we can move forward to the next presentation that is going to be given by Lena Spillecke from the Heidelberg University. And it is an investigation of an erbium-3 plus, say, monomeric complex, probably, like that, strongly anisotropic metal ion. Okay.
Yeah, so thank you very much for this introduction and also for the opportunity to give a presentation here in the frame of this conference. Yeah, so I will talk today again also about high frequency EPR on two novel erbium monomeric complexes. The whole study is a collaboration between the Heidelberg University and several different Russian institutes. So the samples itself were grown in Professor Yakubski's group. The basic squid measurements, so means DC and AC by and the numerics means the crystal field analysis were performed by Vladimir Mironov. I will start with a short introduction, or let's say motivation why we investigate these two molecular complexes. So you see here the molecular structure of the two compounds, and the erbium ion here, the erbium-3+, which is in spin ground state of 15.5, is surrounded in the plane by a pentenyl ligand plane, and there are two acyl ligands here, and especially these acyl ligands can be easily substituted, which is right. The question arises: how can this substitution here actually change or tune the crystal field? And therefore, we investigate two different compounds, which are almost the same in the plane. While for one compound we find a water molecule and a chloride ion in the acyl as acyl ligands, while in the second compound there is the water molecule substituted by an additional chloride ion. Previously performed AC measurements already revealed that for this compound here, we actually see a field-induced slow relaxation of magnetization behavior with an energy barrier of approximately 16 K, while for the second compound here, where this water molecule here was substituted by a chloride one, there is actually no field-induced slow relaxation of magnetization behavior observable at all. And this observation already gives us the first clue that there is actually a change in relaxation behavior, and by this also a change in the crystal field parameters. So in the frame of this talk, I would like to present you how we can trace back this change in relaxation behavior onto the actual crystal field parameters, which were investigated by high frequency EPR. So I will just quickly go over our measurement system. So in our measurement frame, we irradiate the sample with a constant microwave frequency, and we sweep the external magnetic field And yeah, if the resonance conditions are fulfilled, we see an absorption peak in our transmission-like spectra. The microwaves are generated in our system with a microwave network analyzer. With this, we can provide frequencies in the range between 30 gigahertz and 1 terahertz by sweeping the field between 0 and 18 Tesla, and to lowest temperature, we can go to lowest temperatures of 1.7 K. So I will start with my results on EPI results on this first compound here with the 2 inequivalent axial ligands. And what you can see here is a typical shape of an absorption spectra, or the transmission intensity of our absorption spectra. And what I want to mention quickly is that in the frame of this study, we only measured, or mainly measured, loose powder samples, which were oriented with the field prior to the measurements. Why do we do this? Because with this, we can gain much sharper signals. You see here the amplitude of the signal and also the phase information. From these 2 information together, we can precisely determine here the resonance field position. And since the signal is nicely sharp, we can also follow this signal over a relatively broad frequency range. And from a linear fit of the resonance field shift, we can obtain an effective G value of this transition, which is in this case here 12. But so here we explicitly refer to effective 1, effective G value, since we measure obviously only in one direction because the powder is aligned in our measurements. So at lowest temperatures, where mainly only the ground state is populated, we observe only one sharp feature for this sample, which is decreasing in intensity with rising temperatures. However, if we warm up the sample, and by this also states which are higher in energy getting populated, we are also able to measure so-called excited state transitions. And indeed, we see here for our sample that around 8K there is an additional feature popping up, which is definitely not shown at lowest temperatures, which tells us that this is a so-called excited feature. And from following the resonance shift of this feature over a certain frequency range, we see that first of all, this branch here of this blue feature shows a negative slope, and even more interesting, there is a zero field gap of around 800 gigahertz. So from this information, we can construct an energy level diagram. So since erbium has a non-integer spin, the energy level diagram consists of Kramers doublets, which are shifted in energy due to the crystal field anisotropy. And in our model, we describe the Kramers doublets by a phenomenological S = 1/2 pseudo-spin approximation. And for clarity, in this model here, or in this plot here, I omitted the higher lying states. So these are only the lowest 2 Kramers doublets, since within the measurement range of our experiment, we are not able to observe higher lying states. So if we now look at the branches, then we see that this black branch here, which is visible especially at low temperatures, crosses the 0 line, which lets us conclude that this has to be a transition within the lowest Kramers doublet, while this blue branch here figures a zero field gap, which is why this has to be a transition to the next excited Kramers doublet. And by this, we can assign these branches here, or these transitions, to the actual transitions in our phenomenological energy level diagram. From a linear fit to these branches, we can also again extract quantitative parameters. So this here is this G = 12 for the first Kramers doublet, which was already shown on the previous slide. And we can also define the G value for the effective G value for the second Kramers doublet here, which is 9.4. And we can extract precisely the zero field splitting, which is 825 gigahertz for this compound. With this, I would like to show you now what changes if we replace this water molecule here by an additional chloride ion, or how the crystal field parameters change. So again, pretty much comparable to the spectra shown for the previous compound, we find at low frequencies only one sharp feature. However, if we go to higher frequencies, then we see already here that the spectra becomes more complicated. So we see at least 3 different resonance features here. And we can also follow all these features over the almost whole frequency range. So the resonance positions are shown here as black dots. So for this spectra here, for example, at 740 gigahertz, we find these 3 resonance positions here. And we see that we find already at lowest temperatures of 2K at least 3 resonance branches, which are summarized here with R1 to R3. This branch here, which is only slightly visible, this is assigned to a part of the powder which is not perfectly aligned, and thereby this feature here forms this shoulder. But this is an artifact from the powder alignment, so we ignore this for now. But what we see that at least 2 of these branches figure here a zero field gap. And furthermore, we see that branch R1 and R2 figure here an avoided crossing, which tells us that there has to be somehow a mixing of states happening, which is why we see here this avoided crossing. In the same manner as already shown for the previous sample, we measured also here temperature at different temperatures. And we see that, for example, here at intermediate temperatures around 11K, there are 2 features showing up, and also at higher temperatures around 40K. Here we find additional resonance features originating from excited state transitions. And again, we can follow these features in the frequency versus magnetic field diagram. And what we see there is that there are at least 3 branches crossing the zero line, which is why we assume that there are 3 different Kramer doublets participating in which these transitions happen, R1 to R1, R5, R4, like it's numbered here, while there are 3 branches which figure a zero field gap, and by this there have to be transitions in between these Kramer doublets, like it is shown here in our energy level diagram. And from a fit to these branches, we extract again the crystal field parameters and the G values. So these are the G values for the lowest, the second, and the third Kramer doublets. So from here to here. And these branches here in brackets, so these are the branches which we fitted to obtain these parameters. And we can also define the zero field splittings in between these Kramer doublets here to 290 and 270 gigahertz. So this is 290 and this is 170 gigahertz here. For this sample, since we acquired a quite good signal intensity, we also measured a fixed powder to observe the G anisotropy within the lowest Kramer doublet. And you can see here as black line this fixed powder spectra. So we have a relatively high spectral weight on the high field side, while there's a lower spectral weight on the low field side. And this tells us that we expect an axial anisotropy for the G value in the lowest Kramer doublet. And we also simulated the spectra again by this spin 1/2 pseudospin approximation. And by this, we also find quantitative numbers for this anisotropy. So we see that there's indeed an axial anisotropy. So the GZ value here is much higher than GX and GY values. And yeah, this pretty well reflects our measured data. So with this, I would like to come to a comparison of our results and to a summary. So here are listed all the parameters which we were able to extract directly from our HF EPR measurements using this described pseudo-spin S equals 1/2 approximation for each Cramer's doublet. And we see that for the two compounds, the extracted G values for the lowest Cramer's doublet, so the anisotropy, is almost the same for both compounds. However, if we look at the zero field splitting gaps, then we see quite clearly that the gap to the first excited Cramer's doublet is almost 3 times higher than for the compound with the inequivalent axial ligands than for the one with the 2 chloride ions in the axial regions. And this could already give us the answer why we find for this compound here a field-induced slow relaxation of magnetization behavior, while there is not such a behavior visible for this compound. Furthermore, I want to refer here back to this to the slide where I showed that we see for this compound actually an avoided crossing of 2 energy branches, which also tells us that there have to be some kind of mixing present, which also is in line with our observation that there is no slow relaxation of magnetization behavior visible for this compound. Besides, we also compared our obtained values to the results of crystal field analysis done by Vladimir Mironov. And you see here this results from this crystal field analysis in blue. And we see that especially for the lowest Cramer's doublet, the anisotropy, the axial anisotropy is pretty well reflected also by the theoretical analysis. So it's in a pretty good agreement. And also the gap to the first excited Cramer's doublet is in good agreement to the theory. So this works pretty well. However, if we go to higher Cramer's doublets, then it starts to differ from each other. But in the lower Cramer's doublets, it's in pretty good agreement. With this, I would like to give a short summary on my talk. So what have we done? We measured high frequency EPR on 2 novel pentagonal arium compounds. And by this, we were able to determine the G anisotropy within the lowest Cramer's doublet, as well as the zero field splitting between the lowest 2 or 3 Cramer's doublets. And we validated our measurements, or on the other hand, the crystal field analysis, by comparison of experimental outcome to this theoretical approach here. And with this, I would like to thank you for your attention, and I'm open to questions.
Thank you very much, Lena, for this nice presentation and for this interesting presentation, really. I'm wondering, I see one hand that is from Kira, unless it is the remaining from the question before. Kira?
Okay, thank you very much for this interesting presentation. But could you just to show your slide with 2 structures of your complexes, please? This one.
The first one, or?
No, it's okay also.
Okay.
Because at the first presentation, I need some precision about the composition of these complexes. The second complex is with 2 chlorines. There is some cation to compensate the charge of chlorine.
Yes, there is. As far as I know, I have to
Which one?
Remember which was it. So there is. Oh, I'm sorry.
Yeah, because from chemical point of view, I explain that is very important, because if this is organic cation, very large to protect from moisture, because where you're exposing your substance on moisture, the one of chlorides will be replaced by what? If for this reason, during your measurement, you will not know which sample you will investigate. Did you verify your powder composition by powder X-ray diffraction method?
So yes, so the powders were
after the
verified
experiment
by powder X-ray diffraction. Actually, so yes, there is an anion in the complex, but I cannot tell exactly which one. I just remember that there is one.
Yep.
And I also know that the complexes are stable in usual, so they're stable against moisture and oxygen and everything.
But it
so.
depends from the cation, you know. For this
Yeah.
reason, I asked you to precise the composition.
Yeah,
in the future,
not
please know
exactly
the
in
chemical
mind,
formula,
and
please.
yeah,
Thank you very
so
much.
I forgot this. I'm sorry, and yeah, I don't have it in mind exactly, and I don't want to tell anything wrong. So this is why I'm hesitating.
Okay, thank you. Anyhow, if the X-ray powder diffraction after the measurement is the same as the crystal structure, I suppose that you can rely on the integrity of your sample. Matvey, do you have a question? I see your hands up.
Yes, I have a small question. Actually, it's very nice work, first of all. And I have two interconnected questions. First one is, did you, maybe I missed that, did you actually determine how, along which molecular, or better say crystal axis does your powder orient in magnetic field? And this is the first question. And second one is, did you check that it's the same axis for these two compounds? Because maybe crystal packing is a little bit different than something else.
Yeah. Yes, this is actually a pretty good question, and it's also not so simple as to say that they are all aligned along one direction. So the point is, I actually have not a crystal packing diagram. I cannot show it here, but actually there are two directions of the molecules in the crystal packing diagram. I skipped this here for a matter of time. But the point is that we not align the molecules along the easy axis, but so there are two different directions of molecules. So we align along an effective anisotropy axis. This is also why we can only refer here to effective G values, because we actually don't exactly know yet. So it's about to find this out, but we cannot exactly find yet along which direction it is oriented. However, in zero field, so the splittings here are inequivalent, are independent from the actual direction, and also the measurements on the powder, on the fixed powders, where we obtained the anisotropy of the lowest Kramers doublet. They are also independent from this fact that the molecules are actually that there are two molecular sites in the crystal. But yeah, this is a good question. But the molecules are definitely, or the crystallites are definitely aligning, and this we monitor by jumps in the first sweep of our upsweep. So there we see that the powder is aligning, and furthermore we compare fixed powder we compared fixed powder and loose powder measurements, which I can also show here. So, and there you see that there are quite tremendous differences, and this is why we are sure that the crystallites are actually aligned. Yeah.
Okay, thanks.
Thank you very much. I do not see any further questions, so I think we can thank again Lena and go to the next and last presentation that is going to be given by Changhyun Koo. I hope I have pronounced it correctly, about high frequency PR study on 3D4F metal complexes. the contribution is coming again from Heidelberg University, but I see that it is a joint investigation with the Karlsruhe Institute of Technology. Thank you.
Sorry, thanks for the kind introduction, and thank you for the organizing committee to for giving me a chance to present my work in this conference. So here is my presentation. In the single molecular magnet research field, 3D4F heterometallic complex is considered as one of the solutions to improve the molecular magnet behavior. The exchange interaction between the 3D and 4F magnetic moment plays a role in this improvement for the molecular magnet. And so in this talk, I would like to show our EPR, high frequency EPR study on the iron 2 lanthanide 2 complexes for the investigation on the exchange interaction between the 3D and 4F magnetic moments in this complex. Here are the magnetic structure and the schematic. Here is the molecular structure and the schematic magnetic structure. All of the three complexes have the isostructure, and the magnetic ion in the complex show a butterfly-like the structure. So a bonding of the two iron is as a body, and the lanthanide ion positioned as wings. And all the exchange interaction we considered in this talk are shown in here. But the exchange interaction between the lanthanide moments is ignored in this study due to their negligible magnitude. The magnetic property of the iron 2 yttrium 2 and iron 2 dysprosium 2 complexes were reported by the Peng et al. In Karlsruhe Institute Technology already. And the fitting on the Chi-T data of the iron 2 yttrium 2 complex provides the exchange interaction between the iron moments, which is the antiferromagnetic interaction. Also, the Amber's big data of the iron 2 yttrium 2 complex supports the antiferromagnetic interaction on this complex. Among them, the iron 2 yttrium 2 dysprosium 2 complex shows the molecular magnet behavior in the H susceptibility data. With the 1000 Gauss DC applied magnetic field, the chi double prime data shows the peak feature at various frequency and various temperature. Based on this AC susceptibility data, Arrhenius fitting was performed and an effective anisotropy barrier was estimated for the iron 2 dysprosium 2 complex. However, a quantitative study for the exchange interaction between the iron and the lanthanide moment is still missing, and the contribution of the exchange interaction to the molecular magnet behavior in the iron 2 dysprosium 2 complex is not clear yet. So we investigated the anisotropy value of the iron ion and the exchange interaction between the iron and the lanthanide moments in the iron 2 lanthanide 2 complexes. So let's start with the iron 2 yttrium 2 complex firstly. Since yttrium is the diamagnetic ion, we can only concern the anisotropy and exchange interaction for the iron ions. Also, we can use the conventional spin Hamiltonian for the EPR data analysis for this complex. Here are the EPR spectra for the iron yttrium complex at various temperatures. As you can see, many resonance feature appears, and each of resonance shows a different temperature dependence of the resonance intensity. Notify below the 6 Kelvin, there is no resonance feature was observed in the spectra, which implies that the complex would have a singlet ground state. For the convenience purpose, we assigned each resonance feature with the colored labels. the number represents the corresponding the spin multiplet state, and the alphabet represents the transitions in the single spin multiplet state. We will see it later more in detail. From the temperature dependence of the resonance intensity, we can figure out the sign of the d-anisotropy of iron ion in this complex. Here is the temperature dependence of the resonance 1A and 1B resonance feature. The resonance intensity was obtained as fitting on the resonance observed resonance feature with the Lorentzian function. The maximum value of the resonance intensity appears at the higher temperature, which is not in the lowest temperature, which implies these resonance features are excited state resonance. Using the spin Hamiltonian, we can simulate the temperature dependence of the resonance intensity. And when we use the negative d value for the iron ion, the simulated result does not match to the experimental data. But when we use the positive d value, then the simulated the experimental data is somewhat reasonably reproduced by the simulation result. From the EPR spectra at various temperature, we can learn that the complex have the positive d-anisotropy of iron ion and the antiferromagnetic interaction between the iron moments. In order to precisely determine the spin Hamiltonian parameter, we simulate the spectra. Although the resonance intensity is not exactly matched between the simulated result and the experimental data, but the resonance field position are well reproduced by the simulation. In the simulated energy level diagram, we can assign each resonance as the resonances in the triplet state and the resonances in the quintet state. The higher multiplet state is not shown here, but they are also well matched to the observed 3 and 4 resonance features. We can add more concentrate to our simulation with the EPR data at various frequencies. And as you can see in the frequency versus field diagram, the resonance feature show up as the linear resonance branch. The reason why we have the linear resonance branch is we use the magnetic field aligned this powder sample for our measurements. And the simulated resonance branches are well matched to the experimental data. And I will show the spin Hamiltonian parameter, which I use for this simulation. Before that, I wanted to mention just a small remark on this small feature, which is indicated by the black arrow. This is not clearly explained by our current model, but we know this at least the one at lowest field position is the one of the forbidden transition. That's why in the frequency versus the field diagram, we can see the different slope of the resonance branch of this feature. Here is the best simulation parameter. For the exchange interaction between the iron moment, we use the one obtained from the DC susceptibility data. And now we can fix the d-anisotropy for the iron ion and the exchange interaction between the iron moments. For the iron to dysprosium 2 complex, we cannot use the conventional spin Hamiltonian due to the unquenched orbital moment for the lanthanide dysprosium ion. Instead of it, a effective Hamiltonian using the pseudo-Ising spin for the lanthanide dysprosium ion is used for the data analysis. Here is the EPR data for the iron to dysprosium 2 complex at the various temperatures. Interestingly, the resonance feature indicated by the blue square appears from the 2 Kelvin. In the temperature dependence of the resonance intensity, we can see the blue resonance feature shows up the maximum at the higher temperature, which indicates the resonance, blue resonance feature is the one of the excited resonance feature, one of excited state resonance. On the other hand, the ground state resonance is not observed in our spectra at all. So from this result, we speculate that the complex would have the singlet ground state again, but the excited state is quite close to the ground state. In order to see the Hamiltonian parameter more precisely, we plot the frequency versus the field diagram, and here blue resonance feature shows the linear behavior as well. In here, we focus on only the blue resonance branch as the lowest excited state resonance, because we use the pseudo-Ising spin for our Hamiltonian, so we cannot simulate the higher excited state properly. So we only focus on the low energy state. So as you can see, the simulation result is well matched to the experimental data. And this is the best simulation parameter. We fixed the d anisotropy of ion and the exchange interaction between the iron moment from the yttrium to iron to yttrium 2 complex study, and the exchange interaction between iron and the dispersion moment is the ferromagnetic. Even though its magnitude is quite small and weak, but the ferromagnetic interaction is quite important, quite crucial for the best simulation. Indeed, we tried to simulate with the anti-ferromagnetic interaction, but it doesn't give the reasonable result. So from this, we can speculate that the complex has the single state, but the ferromagnetic interaction between the iron and dispersion moment brings down the excited state close to the ground state and open the possibility of the bistability for the molecular magnet behavior in this complex. In order to understand more about the interaction between the iron and the lanthanide moments, we did the EPR, high frequency EPR measurement for the iron 2 gadolinium 2 complex. Gadolinium is not helpful for the good molecular magnet behavior, but we can still use the conventional spin Hamiltonian, which is benefit for the EPR spectra analysis. The EPR spectra for the iron 2 gadolinium 2 complex is somewhat different from the one for yttrium 2 and the dysprosium 2 complexes. As you can see, many resonance feature appears, but do not scattered in the wide field range, but they overlap to each other in the relatively narrow field range. And also, peg of the resonance feature appear from the 2 Kelvin, and especially the sharp feature at the lowest field position has the maximum intensity at 2 Kelvin, which implies that the sharp feature is the ground state resonance. So in order to get the best simulation parameter, we plot the frequency versus field diagram, and the resonance feature shows the linear resonance branch again. In here, we can discrimination between the discrimination of the individual resonance feature is quite difficult due to the severe overlap of the resonance feature. So we only focus on the ground state resonance, and we try to simulate it. And simulation result is well matched to the experimental data. And this is the best simulation parameter. The exchange interaction between iron and gadolinium moment is the ferromagnetic. So here I put all the obtained value in a table, and their magnitude is quite different, or a little bit quite different, but the exchange interaction between the iron and gadolinium and dysprosium has the anti-ferromagnetic interaction. in order to see the tendency of the exchange interaction depending on the lanthanide ion, we compared our data with the one for the other iron lanthanide complexes. For these complexes, the exchange interaction between iron and lanthanide moments are also ferromagnetic, and the exchange interaction between the iron and gadolinium is stronger than the one for the iron dysprosium ion moment, which are consistent to our result in the iron 2 lanthanide 2 complexes. The interaction between the spin half copper and the gadolinium moment is already explained well by the Khan et al. With the charge transfer related mechanism, and we could apply this mechanism for the interaction in between the iron and the lanthanide moment in the iron 2 lanthanide complexes. The 3D electron of the iron ion transferred to the 5D orbital of the lanthanide ion, and by Hund-rule, the spin OD orbital spin is parallel to the 4F moment, which result in the ferromagnetic interaction. So let me summarize my talk. With the high frequency EPR technique, we can unambiguously determine the de-anisotropy of iron and the exchange interaction between the magnetic moments in the iron 2 lanthanide 2 complexes. Although planar type anisotropy of iron ion and the anti-ferromagnetic exchange interaction between the iron moments bothers the molecular magnet behavior, the ferromagnetic interaction between iron dysprosium brings about the slow relaxation in the iron 2 dysprosium 2 complex. And the interaction between the iron and the lanthanide ion in this iron 2 lanthanide 2 complex is reasonably explained well with the charge transfer related mechanism. Now, thank you for your attention and open your question.
Thank you very much for this nice presentation. I'm looking if there are questions from the.
Yeah, I can.
One from Matte.
Thank you very much. I have one small question. Maybe I missed that. Actually, in one of the cases, you determined G value of iron 3 as 1.92. This is a little bit unusual. Could you comment?
True. So I should have mentioned this one actually. So the reason why I put this value for the best simulation is it is from the where is it? This is from the dysprosium. So I can show the dysprosium one. This is from the slope of this resonance branch. So it is not exactly from the G anisotropy of the iron ion individually or separately. It is from the kind of it is try to simulate this effective slope, effective G anisotropy of our data. That's why I put some value for the iron G anisotropy as the 1.92. Also, I should mention in the table for the lanthanide ion, you can see I put some Langdale G value for the simulation because I wanted to fix this G value and try to simulate the resonance plot. So, but yeah, it doesn't bother our result conclusion for the exchange interaction. It is only related to the slope.
Yeah, thank you.
Sorry, just related to the last, to your answer. You have used 4/3 for the G of Landé of the dysprosium, but this implies that you're using the full J15/2 multiplets, while you are saying that you are approximating with an Ising spin. That means you are using an effective doublet state. And in that case, I do not see why the G should be equivalent to the Landé value. Actually, it should depend on the crystal field of the dysprosium. So
indeed,
I don't know if my question is clear enough.
Yeah, it is true. So depending on the structure, crystal fields, the ground state of the lanthanide ion, especially in here, dysprosium ion, can have the various value, not only the just 15 of the 1.33 G value for the, and can have some variance. But from our Embers B data of the iron 2 dysprosium, we think it is somewhat saturated in our field range. And also in our up to the 16 Tesla, which is our available magnetic field, there is no kind of the resonance kink or the curve of the resonance branch. We can only see the linear behavior. So we think that there is no change of the ground state for any of the iron or the dysprosium. That's why we assume we think that the G value and the ground state of the lanthanide ion, which is a dysprosium ion, is 15F and 1.33. That's why. That's our assumption for our study.
Okay, thank you. So if there are no more questions, I think we can thank again all the speakers of this last session. And I give the floor to Matvey for the closing remarks. Thank you, Matvey.
Yeah, thank you very much, Roberta, for chairing this session. And I would like to begin the closing of the conference. And first of all, I would like, on behalf of all organizers, to thank all participants, all speakers, all poster presenters for their very nice presentations. I noticed that normally between 60 to 80 people were listening to each talk. It was a little bit fluctuating, but around this number, 60 to 80, it's not so bad. Some other numbers are that we've had scientists from 14 countries present at this conference, from 10 different time zones. So, you know, we just found some compromise, and also we used recording to be able to a little bit react to this situation of us being in different places. There were altogether 71 talks, including 2 sponsors talks from Bruker Biospin and from Cryotrade. And we once again thank our sponsors for their generosity. And we also have had 29 posters. And as we announced in the opening of the conference, there was some competition, some evaluation of posters. And I would like to pass microphone to Sergey, who will announce the winners of the poster awards.
Dear colleagues, so I should say that we asked several oral speakers to visit all the poster presenters and talk with them and make marks. And finally, this board selected. I just will show the presentation. So four posters were selected for a prize. Krishna Kaushik, Indian Institute of Science, Sujit Kamile, Indian Institute of Science, Olga Minakova, International Tomography Center, and Ivan Zlobin, Moscow Institute of Physics and Technology, and Nismianov Institute of Organoelement Compounds. And there were several possibilities to mention it, and finally we decided to give to everyone, PhD student and student, such a diploma and a book. And so nowadays we can just send the PDF file and transfer the money, but we already so much time spent online, and we decided to prepare a hard copy of this diploma, and we asked the winners of poster prize to send us a link to scientific book which they would like to receive from organizing committee. So we will buy these books, sign them, and send to you to India and to Moscow. So please, within this month, I will write a letter to winners, and please within this month choose the book. We expect that it will be a scientific book in the area of your scientific interest, but it is up to you. Thank you very much, and stay safe.
Thank you, Sergey, and again, congratulations to the poster winners. Please, yes, please send us your requests to the conference email. And I would also like to use opportunity and to thank very much all. Sorry, I will just activate. This slide. So these are, can you see this slide? Yeah. These are people who did a lot for organization of this conference, who were behind all the sessions and all preparations. And of course, many other people also participated in this organization, but I would like to mention especially this team from Nizhny Novgorod, doctors, professors Vyacheslav Kuropatov, Alexander Piskunov, and also Sergey Norkov and Alexander Martyanov. And from Novosibirsk, of course, Sergey Weber, Natalia Artyukhova, and Olga Minakova. They did a great job. And I would like to say that actually much more work was done than was visible, because as you know, in the beginning, we really were eager to organize in-person conference, and many work was done, but it was unfortunately not used. But anyway, I invite you to applause to these wonderful people. And I would also like to thank all chairmen of the conference. First of all, from Nizhny Novgorod, Vladimir Cherkasov and Igor Fedyushkin, also from Novosibirsk, Rinat Sagdeev and Viktor Ovcharenko, and from Japan, Takeji Takui and Katsuya Inoue. Thank you very much for you all for this excellent help in organizing of this conference. And last but not least, or actually not last, just the next, what I would like to say is that the situation now is, of course, unclear with coronavirus and with our future and all these boundaries between countries. But we intend, nevertheless, to organize next conference in Russia in 2 years. So the place and all conditions are, subject to reaction to the circumstances. We shall observe, we shall carefully monitor. We really hope that next time we all meet in person. And I would also like to pass microphone to Professor Takeji Takui to make some comments on next Japanese-Russian workshops. Please, Professor Takui.
Okay, can you hear me, everybody? First of all, I'd like to say congratulations to all of you. I mean, the Russian side. Thank you very much for your great effort and precious time to organize such a wonderful, online conferences. Refer to the next the 15th Japanese-Russian workshop or international workshop. I'd like to say a word about what will happen with the next the workshop 2020 second. If the COVID, the pandemic scenario goes well, better, at least seriously, we'll organize person-to-person or face-to-face based conferences. Otherwise, if a pandemic scenario goes bad, I mean worse, will be organized again at a virtual online conference, like you organized already. But anyhow, so we'll be forced to reform the organization schemes. Probably, I think it's totally. When the organization scheme for the next conference is fixed, we're going to upload the detail on the, the website, on our website, maybe in a few months, okay? Hopefully, we'll solve some financial, this is very important, financial support. Otherwise, probably, so we might stop the organization of the conference from the Japanese side. But hopefully, we will solve the financial problem first. And we're going to, discuss this very important issue among our organizers, from the Japanese side. But anyhow, we'll let you know in a few months. That's all.
Thank you very much, Professor Takui. And I'd like to pass microphone to Professor Igor Fedyushkin on Nizhny Novgorod side. Please activate your microphone.
Sorry, colleagues, yeah. So, dear colleagues, good afternoon. First of all, I would like to thank all the people who provided success of this conference. The success of the conference depends mostly on the program. And to say it more exactly, from the speakers who are invited to give lectures. And in our case, for this conference, the program was assembled, was prepared by our colleagues in Novosibirsk. So they prepared the list of invited lectures and oral speakers. And I would like to thank cordially to colleagues of mine colleagues from Novosibirsk for this excellent program, which we performed excellently. And I hope we will meet us again. Maybe we will meet us here in Nizhny Novgorod. If you are here on business or private, so call us, we will meet you here in Nizhny Novgorod. So you are welcome. Thank you very much.
Thank you very much. And once again, thanks a lot for all the work that was done in Nizhny Novgorod, all the support. That would be fantastic to meet in person there. And we hope to do that still in the future. And I would like to pass now microphone to Viktor Ovcharenko for the concluding remarks and conclusion.
Thank you, Matvey. Dear colleagues, first of all, let me express my thanks to all of you for your valuable scientific contribution to the success of the meeting. We met at an unusual time. It was not the case in our previous life. We don't know for sure what happened in a year, in 2 years. Today, it's really difficult to predict what will happen in forthcoming future. In any case, we will prepare for next conferences and hope the next meeting will be in person. Otherwise, we are in different time zone. Very big difference between Japan and USA. If we speak about Utah and New Mexico, there is 15 years difference. It's not so easy for all colleagues to participate online. For sure, we will stay in contact with Takuya-san and Sato-san, and we'll discuss the best way to proceed. For sure, we'll let all of you to know what we decide, what will be more acceptable to organize next conferences. Thank you so much again. I would like to wish everyone interesting scientific discoveries. Continue to stay healthy and safe. We are closing our conference. Bye for now.
Thank you, Victor. Thank you, Victor.
Thank you.
Please stay safe.
Stay healthy and safe.
Thank you very much. Bye.
Bye-bye.
Bye-bye.
Hey, see you next time.
See you. Bye.
Bye, everybody.
Believe.
Bye.
You bye.